All right, this is our last video in our counting unit in our probability class, and today we're looking at a challenge in the context of combinations. I encourage you to read through this video or read through the problem, pause the video, try this on your own, see if you can do it, and then check back in and follow along. So this is a bit of an abstract problem. I'm asking you to look for some patterns in the outcomes when we do a bunch of combinations calculations. So here's the scenario. You have 5 different objects and you want to make groups of 1, then 2, then 3, then 4, then 5. Okay? And so we're going to just crank these numbers through our calculator, see what we get. But more importantly, we're going to look for some patterns, and then we're going to try to explain why these patterns exist. And then we're going to do the same task with 6 different objects. And let's actually do both tasks first before we look at those patterns. Okay. 5 choose 1 is, 5 choose 1 is 5. Does that make sense? If we have 5 objects and we're only choosing one object, there are 5 different groups, right? There are 5 different single object groups. 5 choose 2 is 10. Okay, that kind of makes sense. 5 choose 3 is also 10. You kind of think it would be more, right? And we'll address this in a little bit. 5 choose 4. Wait, we're back down to 5. And 5 choose 5 is 1. Okay, a little bit of curiosity with the numbers. I'm curious about what's going on. Let's try the same thing with groups of 6. And let's see if we have any more insight. And I'm actually going to add a 0 as well. Okay, and we'll talk about what that means. So we're going to do 6 choose 0. And that's 1. Okay. 6 choose 1 is 6. That makes sense. 6 choose 2 is 15. Okay, we're choosing more objects. We have more groups available. 6 choose 3 is 20. Oh, that's weird. Here from 2 to 3 up top, it stayed the same. But here from 2 to 3, it got bigger. 6 choose 4. Make a prediction before I write it down. It's 15. 6 choose 5 is 6. And 6 choose 6 is 1. All right. So first off, 6 choose 0 is 1, because if you have 6 objects available and you're choosing none of them, there's only one way to do that. You get no things, but there's only one way that could happen. Okay, so that's often a little bit confusing. I think 6 choose 1 makes sense because we're choosing one item, and so there are 6 different single item groups we could get. And these numbers are starting to make sense too. You know, you'd think as you have more items in your group, same thing up here, more items in the group, the number of possibilities gets bigger. But then the question becomes, why are these the same? You should be definitely seeing some symmetry here, right? Here's sort of our axis of symmetry, kind of. And we have 15s, we have 6s, and we have 1s on either side. So I want to explain that to you. Maybe you've already realized it, but here we have 6 objects, and we're selecting 2 to be part of our group. Okay? And here's how I want you to think about this one. Here we have 6 objects, and we're selecting. This might sound kind of mean if we're talking about people, but we're selecting 2 to be excluded. Okay, so can you kind of see that? How it's the same, the number of ways that we could choose 2 people to be included in a group should be the same as the number of ways of choosing 2 people to be excluded in a group, which would then be including the 4 people. So with combinations, but not with permutations, with combinations, you'll always get this kind of symmetry, okay? If you really want to push yourself, I won't show you this now, but explore Pascal's triangle sometime and see if you see this sequence of numbers somewhere in that triangle, or maybe this sequence of numbers somewhere in that triangle. All right, that's a good place to stop right there.